Well, hi everyone, and welcome to this VCE lecture. I'm Dr. Nichole and this is Dr. Hannah Middleton, and we're researchers here at the University of Melbourne. And today we'd like to talk to you about the biggest explosions of the universe, including how we measure ripples in space-time, colliding black holes, cosmological bubbles, and the ancient universe. But before we begin, we'd like to have an acknowledgement of country. The University of Melbourne acknowledges the traditional owners of country throughout Australia. The university recognizes the unique place held by Aboriginal and Torres Strait Islander peoples as the original custodians of country in their continued connection to land, waterways, songlines, and culture. The university respects all Aboriginal and Torres Strait Islander people and warmly embraces those students, staff, elders, and collaborators who identify as First Nations. Today, Hannah and I are standing on Wurundjeri land of the Kulin Nations, and we'd like to pay our respects to their elders, past and present.
Okay, so today we're going to talk about things like black hole collisions, gravitational waves, and looking back in time to the early universe. And to begin with, we'll ask, what do these things have in common? And they all have a common way to try and measure them. And that is what the talk is going to be about.
So the one thing they have in common is interference. They're all measured by interference. Now you can imagine interference as just ripples on a lake, where this person here is taking two objects and bouncing them off the surface of the lake. And as the wavefronts combine when they meet on the lake, they either add or subtract to make either a bigger wave or no wave at all. And if you look closely, you may be able to see some patterns form on the surface of the lake that kind of look like they're radiating outward from the center. And if you were able to look a little bit more closely, you would see these waves, two waves here. The red and the blue waves are the original ones. And when their peaks line up, they add constructively. And when their peaks are anti-aligned, they add destructively. And then they form a new wave, this black wave, that is a combination of both. And you can use this black wave to learn something about the original waves. And light, believe it or not, acts the same way because light is also a wave. Now we're not going to get into the specifics of exactly why that is. It's actually the core of quantum mechanics, and we really don't have time to do a full quantum mechanics course right now. But simply put, light can act as a wave. And so in this GIF here, you have light coming in as this plane wave. And when it goes through these two slits, it then radiates outward exactly like the waves on the lake. And it adds constructively and destructively. So again, if you were to put something at the very end of this box here, you would see a new wave form out of this original wave going through the two slits.
And so interference happens in our everyday lives as well. You can see it when you're walking around the street. So these two examples are things called thin film interference. So one of them is like a soapy bubble, and the other one is oil on the surface. And you can see that you're getting these kind of rainbow patterns. And what's happening here is that you have white light like shining onto the surface of the bubble or the oil, and the different colors get reflected at different stages. So some colors get reflected at the outer surface of the bubble, and some colors get reflected at the inner surface. And then when they're being bounced off, reflected out, they constructively and destructively interfere depending on the color, and I think also the thickness of the bubble or the surface. And that's how you get these kind of rainbow patterns on soap and oily surfaces like these. And you can also hear interference as well. So sound waves can constructively and destructively interfere too. So if you have like sound waves that are constructively interfering, you kind of get this nice harmonious sound, and I'll try and play it now. So it sounds kind of nice, but they can also destructively interfere. And this one, you'll hear kind of beats where it's kind of, you're getting a bit of destructive, listen. Hopefully you could hear that, but you kind of hear it's kind of reverberating in and out as you're getting destructive interference. And also with radio waves as well. So if you're listening to the radio in the car, and sometimes when you're traveling along on the tram tracks, interference can happen due to the tram lines interfering with the signal that your radio is trying to pick up. So that's not sound waves, but it is interfering with the radio waves that the signal is picking up. So how do we use interference to measure something? And we're going to talk a lot about something called an interferometer. So this is interference, and then meter, which is like a measurement device. And as an example, you can use interferometers to measure changes in distance. So this animation shows light going in. You have what's called a beam splitter in the middle, which is like a semi-transparent piece of glass, and it splits the light in two. So half of it goes straight through and half of it gets reflected off. And then these waves are showing like similar to the image we saw earlier with the two sine waves. The light travels down both arms, reflects off the mirrors, and then it recombines. And then we get the combination of those two beams as it comes back onto the screen at the bottom there. And if we have a look at what we see on that screen, depending on the length that the light has traveled down each arm, we get a different offset between the two waves as they come out. And you can see that it's destructively and constructively interfering. It's going from dark to light. And this is a way of measuring relative changes of distance. So if those two arms change distance with respect to each other, we can measure that using interference.
And we can even use this to measure path lengths of the universe. So if you have a source emitting light, like a star up in the night sky, and you have two telescopes that are separated by some distance, the telescope that's closer to the star by, however many meters, will see something different relative to the telescope or the other element that's separated by a small difference. And so you can take those two signals, correlate them together, and get an interference pattern, much like you would using the interferometer with the different path lengths for the arms. And you can actually invert this operation and map the entire sky using this method. And so interference is really helping science go deeper, farther, faster. And it's helping us measure things from the first picture of an atom shown here on the left. This is a hydrogen atom where in the center you have the proton, and the ring around it is actually the probability distribution of the electron. And you can measure the largest things in the universe. So like this first picture of a black hole that you may have seen do the rounds on Twitter and social media. That actually used telescopes spread out across the entire planet in order to measure the very first picture of a black hole. So today we'll talk about how interference is used in astronomy in particular.
Okay, so I'm going to say a little bit about how we use interferometry to find black hole collisions. And this is in the hunt for something called gravitational wave. So I'll explain a bit about what a black hole is and what is a gravitational wave as well as we go. So you might have seen images of black holes like on the movie Interstellar, and like there's lots of various artistic representations of black holes. But what is it? It's like a very, very dense object, which is so massive that not even light could escape from its gravitational pull. And they can be what we call stellar mass black holes, which is small ones which are formed out of the remains of very massive stars, or they can be supermassive black holes at the centers of that galaxy. So in the middle of the Milky Way, there is a supermassive black hole, which is millions or billions of times the mass of our sun, and we think they exist in most galaxies. And so mostly what I'm going to talk about is the smaller type of black hole, the ones that come from very big stars. And how do we search for those? And one way is to look for their gravitational waves. So before we talk about gravitational waves, we'll say a little bit about gravity and how we think about gravity in terms of like a space-time fabric. And this is an idea that's come from Einstein's general relativity, so a theory from 100 years ago. And Einstein thought about gravity like you had space as this fabric that you see in the image here, and objects with mass, they make an indentation in the fabric. And as they move around, they take their indentations with them. And the gravitational waves are ripples in this fabric. So an animation here. So this is in a similar way to the previous picture. It shows the space-time fabric, and you've got two objects with mass moving around each other in an orbit. And as they go, they're producing gravitational waves, these ripples spreading out across the universe. And any accelerating object can make gravitational waves. So if I move my hands around each other, I'm making gravitational waves, but they're so small, you had no hope of detecting them. So in order to find gravitational waves, we have to turn to some of the most massive and most dense objects in the universe, and that is black holes. So we have these black holes that we believe are out there emitting gravitational waves, and we're looking for those signals. But what does the signal look like? What exactly are we looking for? Okay. And the answer is they change distances a little bit, a tiny bit. They stretch and squash. So if you look at this animation on here, you can see a gravitational wave that's sort of traveling along. And as it goes, it's changing the shape of those rings in the blue kind of worm-shaped thing. And if we were to look at it face on, then we can see how it would look at the bottom of the screen there. So initially it would be a circle, and then they'd get squashed one direction and stretched the other, back to a circle, and then squashed in the other direction and reversed. And it would keep repeating as the gravitational wave passes through. So we've got this gravitational waves that are making very, very small changes in distance. And we have also interferometers which can look for changes in distance. So this is exactly what we do. We build interferometers that are able to search for gravitational waves by looking for the tiny changes in distance that they make. So I'll come back to this animation again, and this is a very simplified version of how the real detectors work. And the detector is called LIGO, and it stands for the Laser Interferometer Gravitational Wave Observatory. So it's using light and laser light to search for gravitational waves by looking for the distance change that they make. And we've got a little demonstration here to show how that works. So, I guess you can come up at the end as well and have a little look at it. But what you see here is there's a laser over at this side, and so the laser's shining this way. It moves, it turns the corner. This is just a mirror to make space on the board. And then we have the beam splitter here, which is the same as the beam splitter that we see on this image up here. Then you've got the two arms, which are going like this direction and this direction. The light travels down both arms, and it comes back to the middle, gets reflected off these mirrors, and then it recombines, just like we saw at this part of the animation. And then when it recombines, you get this interference pattern, this dot in the middle here. So it's probably a little far away for you to see, but come up at the end. But what happens is if I... Oh. Is it better? So what happens is if I just push gently on the back of one of the mirrors, I'm changing the distance between one of these arms, changing the distance, the relative distance that the light has travelled, and it changes the interference pattern. And you can see the rings sort of going in and out there. But the idea is that we build something that is incredibly sensitive and much bigger and more complicated than this, and we can find the gravitational waves that change the distances between the arms of the detectors. So that's how the like a simplified version of how the real detectors work, but in reality they're much bigger and much more complicated. So I guess, should I turn the light back on? Oh yeah, definitely. Go and have a look. So there, we couldn't really see how much I was changing the mirror. Like I was just gently pushing on the back of it. And with our eyes, we can't see any change in distance. And with gravitational waves, for sure, we would not notice any change in distance at all. But the detectors themselves are much bigger. So this is along the side, there's 3 images of different detectors. There's LIGO Hanford and LIGO Livingston, which are both in the US. And both of those have arm lengths that are 4 kilometers long. So on here, what's a few centimeters, in them is 4 kilometers long. And Virgo is another detector in Italy, and that one is also very big. It's 3 kilometers long. And the schematic at the top you can see is a closer representation of what's inside these detectors. So you have the laser at the top corner, at the side here, and then the 2 arms, but there's a lot more that goes into making them incredibly sensitive. And they have very big mirrors as well. So these ones are just like a couple of centimeters big, but this is the size of the real mirrors in the detectors. And all of that is to make them as sensitive as possible. And after producing these detectors and searching for gravitational waves, we have actually found gravitational wave signals. So the first detection was in 2015, and it was a black hole merger. So 2 black holes, and each one was around about 30 times the mass of our sun. And they collided, and they were about 1 billion light years away, and their gravitational waves spread out, and then they eventually reached Earth, and they wobbled our detector, and this is the signal that we pick up. So this is from the data from 2 different LIGO observatories, LIGO Hanford and LIGO Livingston at the top and middle. And then at the bottom, you can see that the 2 signals overlap really well. So this is, it shows time in seconds on the x-axis. So you can see it was really short, like a really short signal. And on the y-axis shows strain. So it tells you how much your detector length changed. And we can also listen to how this signal would sound. So by looking at it, you can see that you've got a signal that gets louder over time because the amplitude increased. And it also gets higher in frequency over time because the peaks get closer together of the wave. So what's going on there is the 2 black holes are orbiting each other, just going along, but they get closer and closer together and faster until eventually they merge. And then everything goes quiet at the end. So that's what you see in the image there. And we can listen to how that would sound. So this is going to play kind of 2 sounds. One is like the natural frequency of the gravitational waves, and then it shifts it to make it sound a little bit better to our ears. So what you're hearing there is this like whoop kind of thing, where the frequency is increasing and then it goes quiet when the 2 black holes have merged. And they've produced a new bigger black hole at the end. So that was the first detection, and it was, so the naming is kind of unimaginative, as some astronomy naming is, I guess. It's GW for gravitational wave, 15 for the year, so it was in 2015, and then September the 14th. So that's what the numbers mean on all of the observations. So there's been a few observations since then. And one of them, very excitingly, was that 2 neutron stars collided. So neutron stars are a little bit different to black holes. They're very dense as well, but they're not so dense that light can't escape. And this one was very exciting because you can also get light from these observations too. So if two black holes collide, we're not expecting to see any light from that collision. But if two neutron stars collide, then we can pick up light as well. So various different electromagnetic telescopes all around the world also looked, and they found the signals from the two neutron stars colliding in their own telescopes too. And then more recently, we found gravitational waves from the biggest black hole collision so far that's been seen. So this one was around about 85 times the mass of our sun. That's what this symbol means on here. And it collided with something that was about 66 times the mass of the sun. And then the final black hole was about 142 times the mass of the sun. And this was the biggest black hole merger that we've seen so far. But there's heaps of black hole mergers out there. So this graphic is showing all of the gravitational wave observations that we've managed to see so far. And on the scale, it shows the masses of them. So this is in like number of times the mass of our sun. So our sun is one times the mass of the sun. And then each merger shows two black holes which merge and then form a third bigger black hole. Or these ones at the bottom are neutron star mergers. So there's lots of work being done to understand what are the properties of all of these black holes, and can we understand like them as a population rather than just individuals. But it's not stopping just there. So you can also search for other types of gravitational wave signals. So if we were to have our gravitational wave shopping list, we know we've got our colliding black holes and we've got our colliding neutron stars. And there was a possibility that one of those was a neutron star colliding with a black hole, but the lighter object, the neutron star, was a little bit uncertain about what it was. But we can also look for things like spinning neutron stars. So a neutron star just spinning on its own makes gravitational waves. And the group here is doing a lot of work to try and find those. And you can search for things like supernova explosions and many overlapping signals as well. And of course, surprises. So every time you build a new telescope, you kind of hope to see something that you weren't expecting at all. So in the future, there'll be more detectors on Earth. So the map is showing various detectors that are planned or already constructed or underway. In Japan, there will be a detector built underground inside the mountain called Kagra. And there will be a LIGO India, which is coming soon. So the site has been chosen for LIGO India, and construction will hopefully start pretty soon. And then we can also put gravitational wave observatories in space. So this is going to be an observatory called LISA, which searches for lower frequency gravitational waves than LIGO can detect. And it will be like a constellation of 3 satellites that fire lasers to each other over millions of kilometers. And you can also use pulsars as gravitational wave detectors to build a detector on a galactic scale. So pulsars are stars which emit a beam of radio light every time they rotate. So they're like the lighthouses of the universe. And people are using them to try and pick up gravitational waves from supermassive black holes. So much, much bigger black holes than what we found so far. So there's a few places if you wanted to find out more about gravitational waves. There's a few like free games and apps that you can get on your phone, and also LIGO magazine as well, to like hear about stories from LIGO scientists. And now I'll pass over to Nichole, who's going to tell us all about the early universe.
Thanks, Hannah. Yeah, so in a slightly different vein, I'm going to take us on a journey into the early dawn of our universe. And specifically, I'm hunting for the epoch of reionization, and I'll let you know how far we've gotten in that search. But first, I have to give a little brief history of the universe. This is a artist's representation, obviously, where it starts with a big bang. We don't quite know why it happened. We don't know really how it happened. It just happened. And it's one of the biggest mysteries in the universe, and we're trying really hard to understand it. But in order to understand the Big Bang and everything else that happened in the universe, we need cosmological models that describe our universe with math. And so hopefully we'll be able to extrapolate the math down to the Big Bang. So we kind of need to understand all of the phases of the universe to really make our models the best that they can be. So after the Big Bang, not much was happening. There was just this gas that formed about 300,000 years in. It was mostly hydrogen gas. And we call this the Dark Ages. It lasted till about 500 million years into the age of the universe. We call it the Dark Ages because there were no stars, there were no galaxies, just gas floating around. And over time, gravity pulled this gas together to form the first stars and galaxies. These first stars and galaxies emitted harsh UV light that kicked off the epoch of reionization, which I'll tell you more about in a minute. But the epoch of reionization is essentially the last phase change of the universe. This is the last time the universe was different. After that, you essentially have modern day galaxies and mergers and the stuff that we see when we look up into the night sky. So we want to look back in time to this epoch of reionization. And this is what we think it may have looked like. So in the red here, you have hydrogen gas floating around. And these white dots are the first stars and galaxies. And as they form, they emit harsh light that rips apart the surrounding hydrogen. So it rips apart the electron from the proton. So you go from this gas that we've colored red here to essentially nothing, essentially a dark universe. So this is a very interesting time period because of all that structure that we saw, all this like weird Swiss cheese structure. We want to be able to look back, see this Swiss cheese structure, and it will tell us a multitude of different things about the universe and our cosmological models. But how do you look back in time? Well, we're going to use a trick. So we know that this leftover gas is hydrogen. And we also know that in atoms, they have something called spin. It's a quantum mechanical property. And so the proton will have a specific spin and the electron will have a specific spin. And it's usually up or down. And so when the hydrogen has a proton spin and an electron spin that's up, it's in the ground state, that's fine. It's not doing much. This is pretty much the most uninteresting atom that you could possibly have. But every once in a great while, the electron will flip its spin. It's a very, very small probability that this will happen. But if it does, it's changed its energy state. And so it releases a photon of light. And this photon of light has a very specific characteristic wavelength, has a very specific wave to it. The other piece of information that we need to know is that the universe is expanding with time. So during the Big Bang, right after the Big Bang, the universe was actually quite small. Today, the universe is unimaginably large. And we think dark energy is the cause for the expanding universe. Again, we don't quite know what that is, but we're trying to figure that out. So if the universe expands, the light also expands with the universe. So you can kind of imagine the light being a rubber band that has been stretched. You haven't added anything new to the rubber band, you haven't added any material, but you have changed its length. And that's what's happening to the light. So light becomes redshifted, or it becomes more red. So if you had blue light that you could see as the color blue, over time as the universe expands, it will become red light. So that's why we call it redshifted. And so if you have a hydrogen atom that undergoes a spin flip at a specific time in the universe, it emits that characteristic wavelength light. And as the universe expands with time, that light also expands. So by the time you've measured the light, it's at a different wavelength. But if you have a hydrogen atom that emits this characteristic wavelength later in time, what you measure is going to be closer to that original wavelength. And so if you know that you're looking at hydrogen atoms, you can use the wavelength that you've measured to determine at what point in time that light was emitted. And so we're going to use this to actually look back in time at the gas. Since we know what its wavelength was to begin with, we can do this. You can't just do this with any old light, but given that we know what it was emitted at, we can reconstruct what happened or when it happened. The issue here is that it's incredibly faint. The signal that comes from this hydrogen gas, it would be like trying to see a light bulb on Pluto in the middle of a fully lit gigantic stadium. So this is one of the most difficult things that astronomers have decided to measure, along with gravitational waves. But we're starting to get there. We think we can actually measure this signal, but we need extremely large telescopes. And one note is that light comes in a variety of different wavelengths, and things that you think might not actually be light are light. So X-rays are light, and radio waves are also light, which is kind of weird because when you hear radio, you think the thing that you hear coming out of your stereo, but actually your stereo is picking up this wavelength of light and converting it into sound for you. And so if you have light that was emitted in the early universe and the universe has expanded over time, it makes the wavelength longer and longer and longer. And so we expect that the wavelength of light that comes from the early universe should be in the radio waves. And so that's where radio telescopes come in. This may seem familiar. Parkes is in our backyard. It was featured on The Dish. You also have these gigantic radio telescopes. This is one that was recently built in China. It's called FAST. It looks a lot like Arecibo, rest in peace. And these large dishes get finer and finer resolution and measure more and more light so that you can see this really faint signal. But the issue is that large dishes are extraordinarily expensive and almost logistically impossible. So, I mean, that's why Arecibo caved in on itself. It's so expensive to uphold that if you don't have the right funding streams coming in, you may lose your billion-dollar project. So the way around this is to, rather than build the entire dish, just build bits and pieces. The bits and pieces that still get you the same resolution, maybe not the same sensitivity. You may have to look for longer, but you can still essentially make this gigantic dish by just building bits of it. And that's where interferometers come in. So this is the concept behind building multiple dishes around the world that you can then take their signals and correlate them together. So if you correlate together the two signals from these two antenna in this GIF here, it would essentially be like you having built an antenna that spans the entirety of these two dishes. And this is very analogous to the interferometer that Hannah showed earlier, where we're measuring a path length. And the path length that we're measuring is actually the difference in the plane wave that's coming in from the light on the sky. So if you have a source that's emitting light, as it comes in, it will hit one element first and then the next element. And the pattern that you get out at the end depends on how far apart the antenna were and the path length of the light from the direction on the sky that the light source came from. And you can build up these interferometers. So you can have essentially a two-arm interferometer that I'm showing schematically here, where instead I'm showing like slits instead of arms. So you can have two. That's the most basic interferometer. It gives you one interference pattern. If you bump that up to 3 slits, you actually get a variety of different waves. And if you bump that up to 4, you get even more. And these waves are actually composite of all of the individual correlations done between the slits. So on the biggest scale, between the 2 slits at the very edge, you get this wave that I've highlighted in red. But you also get a signal from these antenna, which gives you a slightly different wave. These antenna gives you a different one, and that, so on and so forth. And so you can see that as you build up the number of elements in your interferometer or the number of slits, you get you quickly get many, many, many waves. And if you add these waves together, you are reconstructing the sky. So the source that I put in was a delta function, and you can see that with 4 elements, I'm quickly converging to the thing that I put in to begin with. And this in of itself is kind of a simple concept that we actually have not been able to implement until maybe a decade ago. And that's because you need one of the fastest computers, superclusters in the world to combine all the data. So if you have 1,000 slits, you'll have an enormous amount, millions of different waves that are coming in that you need to combine. You need to do it as quick as the data is coming in. And so you need to have essentially these gigantic brains attached to your interferometer in order to keep up with the data load. And so I work on a radio interferometer that's based in Western Australia. It's called the Murchison Wide Field Array, and this is what it looks like. It's 128 individual tiles spread out across the Australian outback to many kilometers in distance in between them. And you can see that they don't look like dishes, but they still act like dishes. So they actually look more similar to your classic TV antennae that you used to put on top of a TV that you would like mess around to try to get the signal. And that still gives you, it still picks up radio waves, even though it's not dish-like. So each one of these little, we call them spiders, they cost $100. And so you have a couple thousand of them spread out. And so you can build something as sensitive as Arecibo with a pretty tight budget, as long as you have a supercomputer, which is not a given. So if you could see with your eyes what the Murchison Wide Field Array sees, it would look something like this. So this right here is the optical. This is what we see with our eyes: stars, galaxies, a little bit of light on the horizon, nothing special. And here in a second, it'll switch back to what the radio would look like, where we've colored it artificially for your benefit. You see this streak, that's the galactic plane. That's our own galaxy's gas emitting radio waves. You see some bright sources of light. Those are gaseous galaxies. And I will note that every single dot here is a galaxy. There are no individual stars that you can see. You're actually looking at the expanse of the universe through one of these images, billions and billions of galaxies. And so this has been really a fascinating project to work on, because even though I work on the early universe, I get to see stuff from the nearby universe, in fact, our own galaxy as well. That's kind of a problem, because if I want to try to look back in time and all I see is our galactic plane, that can be a bit of an issue. And so this is that galactic plane. Again, lots of great research has come out investigating how that looks in the radio. There's been a lot of research on nearby galaxies and how they look in the radio as well. We've seen things that go bump in the night. This is in fact just the moon, but we have seen a variety of different transitory things go by that we don't know what they are. But we have not seen the EOR. That is still a work in progress. And it's still kind of a work in progress because of all these other things are in front of the epoch of reionization, and we need to remove them from our image in order to see the EOR. So the race is on. There are instruments around the world that are trying to measure the epoch of reionization first. 3 in particular, one in the Netherlands, one in South Africa, and of course the one in Western Australia. And in Western Australia, we're actually starting to construct something called the Square Kilometre Array, which is going to be massive. It's going to take the Murchison Wide Field Array and expand it over 100 times. It's going to be built of many, many little antennae, 130,000 specifically. It's going to be spread out over 65 kilometers. And it's going to be, it's going to build such a computational load like we've never been able to manage before. We're going to be having to take in 157 terabytes of data per second. So that's 4.9 zettabytes a year. I don't even know what a zettabyte is. It's massive. But I do know it's enough to fill 35,000 DVDs every second, or it would give you the estimated global internet traffic in 2015 per year. And so, right, we're also building some of the world's best supercomputers to handle this input data stream. And it's really going to push our ability to handle such volumes. It's going to really increase our infrastructure. And we hope that the things that we build for the Square Kilometre Array, the technology that we develop in order to handle stuff like this, will end up on your phones one day, let's say. And so once we build the Square Kilometre Array, we will almost certainly be able to finally measure the epoch of reionization. And when we do that, we'll be able to learn a lot about the astrophysics of the early universe, like what were these first stars and galaxies? We've never actually been able to see them. And how did they form from essentially just hydrogen gas? From a cosmological standpoint, we'll be able to learn many things about what dark matter is, what dark energy is, some of the greatest mysteries in the universe we'll be able to shed light on with the Square Kilometre Array. And so interferometry really is the future of science.
So we've been able to use interferometry to search for things like gravitational waves, which just make very, very tiny changes in distance from some really massive black holes. And so thanks to interferometry.
And we're going to be able to measure things from the early universe, be able to look back in time. So thank you for listening.
Does the Does the universe have a boundary if it's expanding?
That is a fantastic question.
Repeat the question.
So the question is, does the universe have a boundary if it's expanding? Theoretically, yes. There's something called a event horizon, essentially, but for the cosmological scale, where light travels at a very specific speed. And so you can only look back as far as time has allowed that light to travel. So I don't think we'll be able to ever see the boundary of the universe. It's actually not theoretically possible to see it, though there should hypothetically be a boundary. Do you agree with that?
Yeah.
That was a hard question.
We actually know what that wavelength you're looking for. It's like a specific wavelength, isn't it?
Yeah. So we know what wavelength that we're looking for the hydrogen atom spin flip. We know it extremely precisely, not because of astronomy, but because it's used in like condensed matter experiments and other realms of physics. They've measured that wavelength very, very, very finely. It happens to be 21 centimeters. Something, ish, right? Like roughly that big. And without that, we wouldn't be able to, without that knowledge, we wouldn't be able to look back in time. So it's extremely important to know what the wavelength was to begin with.
I've got a question from Benita. She asked, what are the limits of distance interferometry can measure? Sorry, what are the limits of distance interferometry? How small would be 29?
So the question was, what are the limits of interferometry? Like how big or small can it measure? Do you want to talk about the big?
I guess from the library point of view, we can measure changes in distance that are kind of like measuring, I think it's from here to the nearest star to the width of a human hair, to that kind of accuracy. And when we're searching for gravitational waves, the change in distance we've seen is like, I'm trying to remember the number, but I think it's a change that's on the scale of like 10 to the minus 21, something like this. So it's very, very, very small.
And from the telescope's standpoint, currently we're kind of limited to the Earth. So we can take two dishes, put them on the opposite side of the Earth, and that would be the longest path length difference that we could then use to measure things in the universe. But that's not really a limitation. There's a lot of people talking about putting something on the moon, maybe shooting something out into space. The only issue with that is that we need to be able to get data from whatever we shoot out into space or put on the moon. So it's definitely a possibility, and the sky's the limit in that regard.
How far back in time do you expect that rate that we see?
Say that again?
How far back in time do you expect to be able to see the wave?
Oh, so I'll answer for me. So with the Murchison Wide Field Array, where we measure radio waves, we can see to the dark ages. So we can see to when there was nothing, which is actually really surprising, well, really exciting, because you wouldn't be able to look back in time and see those stars or the absence of stars in the dark ages, but there's gas floating around in the dark ages. So we expect to be able to see that gas. However, at least for the Murchison Wide Field Array, you can't really look further because of our own ionosphere on the Earth interacts and it starts to sing at roughly 10 megahertz. And so we can't look beyond that because we're currently stuck on the Earth. But if you were able to put something into space, you might be able to see even further.
I guess from the gravitational wave point of view, we can sort of, it depends how loud the signal is. So if something's very loud, or so like if the masses of the two black holes are particularly high, then we can probably see that from like a bit further away, because it made a louder signal in the detector. But as we kind of improve the detectors over time, we should be able to see further and further. But it's not as far as the epoch of reionization. It's because black holes wouldn't have necessarily had time to form at that point. But we see, like, yeah, it depends on the strength of the signal.
I have a follow-on question for you. And this is the answer that I usually give when someone asks that question, like, oh, could you see the Big Bang? Well, not with light, because the universe was actually a soup, essentially, to begin with, and you can't look into soup. You can only see the surface of soup. And so for radio waves and stuff like that, we're stuck. But I've heard that you can use gravitational waves to maybe look at the Big Bang. Is that something that we can even do, hypothetically, theoretically?
So I think possibly. I mean, I don't know for sure. I know you can search for like the imprint of gravitational waves, like on the cosmic microwave background.
Oh.
But and I think you perhaps you could pick up gravitational waves traveling through the gas. But yeah, I'm not totally certain actually.
It's very theoretical at this point.
Another question. Do gravitational waves have a wave-particle duality like light and electron?
Oh, wow. So the question was, do gravitational waves have a wave-particle duality, like light? And so they're a different kind of wave, but so we kind of imagine them as like like ripples on the surface of space-time. So in that way, we're thinking of them like a wave. But there is also a theoretical particle called a graviton, which so my particle physics is not the best, but it hasn't been found yet. So I guess in a way there is this thing that's kind of like the photon in the graviton, but it hasn't been observed yet.
So according to the conservation of energy can't be created or destroyed. Where did the energy come from during the Big Bang?
We don't know because we can't measure it, but there have been some mathematical models that there's been quite a number of different theories. One of them is that we live, the universe is on a membrane, and whenever the membranes slap together, a Big Bang happens. That's my extent of knowledge of that theory. They start to get really, really technical really fast. But yeah, there had to be some sort of energy expansion. Some things should have happened. One of the ideas is that like maybe there was like some sort of decoupling event where all of the forces, so like the force of gravity, electromagnetic forces, all of the very strong, weak forces, they used to be a singular force, and that they split almost instantly after the Big Bang. So maybe there's something regarding the forces, maybe something happened to them, maybe we were in kind of a unstable equilibrium, and then a small quantum fluctuation pushed us in one direction and we exploded. We don't know.
Hey, thanks again to Nichole and Hannah, and thank you so much.
Yeah. Thanks everyone.